Hello, my name is Tatiana Kuvshinova and I'm presenting a research on sentence compression for Russian, the dataset and baselines. Sentence compression is a text-to-text writing task of shortening a sentence by omitting redundant information while preserving the main points. I will cover deletion-based sentence compression. In deletion-based sentence compression, a verbose sentence is converted into a neat one by deleting some of the words without reordering or inserting aberration. So we can remove some of the words, but we do not add or modify any other words. And on the slide you can see an example for English where some of the words were removed and the remaining form a compression. And as you can see from the slide, deletion-based sentence compression is often viewed as a binary classification task. When we classify a source sequence of words by delete or stay labels and then remove those with delete labels. So for English there are a number of approaches such as syntax tree carting, interlinear programming, and over the recent years the most popular is using different recurrent neural network for compression, so the data-driven system. But for Russian, as far as I know, there were no previous research made, and this is the first research of sentence compression in Russia. And as the sentence compression task can be solved and is usually solved in the modern system in a data-driven way, I have also came to it with a data-driven solution. So firstly, I had to collect and create a corpus for sentence compression in Russian because the task was unapproached before and now corpora were available. So I used firstly the data from Russian paraplag corpus, that's a Russian plagiarism corpus which was released on a dialogue conference several years ago. I selected it in a necessary way. I will describe it in the following slides. Aligned sources to compressions word by word using Needleman-Wunsch algorithm for sequence alignment, and provided human evaluation of the data quality. I also prepared this data, making it compatible with Rus Victoria's open source embedding models. And I made the data publicly available. You can see the link on the slide and click it in the presentation. And then to directly sentence compression, I trained a long short-term memory network baseline for sentence compression and also Russian BERT and multilingual BERT models. And with the multilingual BERT models, I also experimented with transfer learning for sentence compression in Russian. I provided not only automatical, which goes without saying, but also human evaluation of results, which is very important for sentence compression task. And then I implemented a syntax-based Posthoc evaluator of compressions. So this was a quick outline of my work, and in the following slides I will cover it in details. So firstly, about the data. A paraplag corpus is a plagiarism detection dataset. A plagiarism is often a result of compression or elaboration of the source. So when a person wants to plagiarize something, he or she deletes some of the words from the source or expands it, mainly to cover plagiarism. And it contains around 7,000 sentence compression pairs which are annotated in the corpus. So the cases when a person removed or added some words from the source sentence are annotated in the corpus, and we can take them and use as sentence compression pairs. And you can see an example on the slide. So this is the source sentence. Это не из-за того, что он замкнут или не выносит журналиста, все на самом деле сложнее. And in compression sentence, some of the words are removed, but none of the words are reordered, and no new words are inserted. So, but sometimes a person plagiarizing a sentence will not only remove or insert some of the words, but will also paraphrase some of the other words. And you can see an example of the slide when in the source sentence we had книги Толкина послужили, and then it becomes книги Толкина стали. And for such cases, I resolve the paraphrase before adding compression to the corpus. And in cases where it wasn't clear how to automatically resolve the paraphrase, I removed these pairs at all. And after resolving paraphrase, I had to align word-to-word sentences to their compressions to understand which concrete words were removed. I used Needleman-Wunsch algorithm for sequence alignment, which was primarily introduced for DNA sequence matching, but is sometimes used in computational linguistics also. And in the result, I received an alignment where some words of source sentence were aligned to them in compressed sentence, but some source words are aligned to none or zero, so it can be said that these words are removed. Then I selected only compressions with at least 1.7 compression rate. This means that I only use the sentences where at least 30% of words were removed of original tokens. And the reason behind this decision is that in those sentences with very high compression rate, where only a few words were removed, some of the words which could be removed were not. So this data forms a very poor training material because it's inconsistent. And then I made a train test split, which I also make available, and the result is almost 3,000 pairs of sentences, and you can see statistics on them on the table below. So number of sentences in train and test set, and the number of tokens in each set, and compression rate. Then I had to evaluate this data to give the idea how good it is to use in sentence compression task to solve it. And I provided human evaluation of the data by readability and informativeness, which is traditional metrics of human evaluation for sentence compression. 3 native Russian speakers evaluated these sentences using a 5-grade scale, and where 1 corresponded to completely unreadable and uninformative compression, and 5 corresponds to perfectly readable and informative compression. And you can see that result is a mean readability of 4.68 and the mean informativeness of 4.03, which is rather good. It's comparable with results of human evaluation of English sentence compression corpora. And my experiments, firstly, I decided to build a bidirectional long short-term memory network because it's a classical baseline approach for sentence compression task, which is usually used in any research covering sentence compression in English now, and any other model is compared to it. And I built a 3-layered bidirectional LSTM network with input and hidden layers of 300 dimensions, because that's dimensions of Ross-Victorious models which I used, and the softmax output layer. I used binary cross-entropy loss function and Adam optimizer. And as I have already mentioned, I have used pre-trained embeddings from Ross-Victorious to initialize the model. And I also have trained 2 more complex models, such as Russian BERT and multilingual BERT. For Russian BERT, I added a linear classification layer on top of the BERT and used cross entropy for the last function. For multilingual BERT, I use the same model architecture as for Russian BERT, but firstly I fine-tuned the model on 8,000 English sentence compression pairs of Google sentence compression dataset, and only then trained it on Russian sentence compression pairs. So I used transfer learning for the task. And I will cover the results of my experiments later, because it will be easier to summarize. And now I will speak about Posthoc syntax evaluator. Firstly, why do we need it? Because after the compression system works, there inevitably are mistakes. And in a ready-to-use system, we wouldn't like to see them. And that's why I decided, inspired by 3 cutting approaches to sentence compression, to build a syntax evaluator which will decide whether the sentence was grammatically compressed. And the main idea is that it's ungrammatical to remove a head, preserving each child. So the compression graph ought to be a subgraph of the source graph with the same root. So you can see an example of the slides. This is a sentence, сокращая предложение, будьте внимательны, and it's syntax dependency graph. So you can see that if we remove some of the words, we will get compression anyway, but it could be a wrong compression. And potentially correct compression is achieved by removing its leaves, such as предложение or очень. Then we get a correct compression, сокращая, будьте внимательны. But if we remove a note, but its child stays, then we get a wrong compression, such as сокращая предложение, будьте очень, which is ungrammatical. So the main idea is we wouldn't like to remove notes when the leaves are staying. We should remove the whole branch if we want to. And if the compression system has removed something like in this example, it is probably wrong, and we have to do something, at least remove this compression from the result. And for building syntax evaluator, I used universal dependency syntax parser and Russian UDPipe syntax model to build dependency trees. And then I counted tree distance, so it's a number of nodes that have changed their parents after compression, and ideally none of the nodes will change their parents, so they will stay with the same parents. But if their parents were removed, such as this example, they are forced to change their parents somehow, and that's wrong. And then I normalize the tree distance all over a number of words in compression. And on this slide you can see the tree distance distribution of the trend set. And you can see that most of the sentences have zero normalized resistance distribution, which is great because train set sentences are supposed to be correct with no wrong compressions. However, some of the sentences pairs have not zero to resistance, and that doesn't necessarily mean that compression is wrong. It can be because the syntax evaluator have mistaken, because the syntax parsing is a hard task, and it can also be a result of particular cases where in universal dependency theory dependent is chosen in such a way that it actually can stay when its head is removed. So by analyzing this graph and also concrete examples of sentence compression pairs with different tree distance, I have chosen a threshold of 0.1, and that means that compression with high proportion of misplaced nodes are considered wrong, so they are not correct. Unfortunately, now I have no way for correcting these wrong compressions, but I can simply not compress them. So it works like a Posthoc evaluator, which shows cases where compression went wrong and says that we just don't compress the sentences. And on this slide you can see evaluation results. Firstly, automatic evaluation for all the models themselves and models with syntax evaluator. And let's firstly look on just models, which are in this light cyan color. Long short-term memory network, Russian BERT, multilingual BERT. So firstly, what multilingual BERT-RU is a multilingual BERT model which was trained only on Russian corpus, and multilingual BERT is a model which was pre-trained on 8,000 English sentence compression pairs from Google research dataset, and then fine-tuned on Russian sentence compression pairs. And you can see that surprisingly LSTM outperforms more complex approaches such as Russian BERT and multilingual BERT. And while I have no ideal explanation why does it happen, I believe that the reason is that a relatively small amount of training data which we have for such a complex languages for Russian doesn't allow to complex model to better generalize, and long short-term memory network which I use is initialized with weights of Rus Victorious pre-trained vectors with part of speech tagging, so it has like more information maybe initially than Russian BERT, which was supposed to to be good and to learn this information because it's a pre-trained BERT model, but maybe then there were not enough training data for the task to adapt. So, but another interesting point is that we can see that multilingual BERT model outperforms the model trained on only Russian data. So we can see that by combining training it on English data and Russian data gives us a 2 percentage points rise in quality, which is rather good. And this effect was observed for the natural language processing tasks and multilingual BERT model, but it is very interesting that we can see there because it shows us the promise in using transfer learning for sentence compression tasks. And then about human evaluation, again, as evaluation of the goal data, 3 native Russian speakers, the same one actually, evaluated all the system's compressions by readability and informativeness using a 5-grade scale. And they represented compressions, sentences and their compressions, in a random order, so they wouldn't know which systems they are evaluating. But they would see several compressions to one sentence and evaluate them accordingly. And on the slide you can see an agreement rate between annotators. I consider it satisfactory. Then these are results of human evaluation, and you can see that I also have gold compressions on the slide to compare it, and you can see that in this case, despite the fact that long short-term memory network have shown the best automatic evaluation results, it is showing lower human evaluation scores than multilingual BERT model. And I would like to emphasize that human evaluation is very important in sentence compression task, because we can achieve like a 19% accuracy, for example, by removing 2 random words like subject and object, and the compression would be absolutely unreadable and uninformative, so it would be basically wrong and unusable, and then automatic evaluation results could be just great. So human evaluation results is definitely more reliable and should be provided also for the task. And we can see that despite the fact that we had LSTM baseline as a leader in automatic evaluation, apparently multilingual BERT model is better in compressing sentences. Then about applying a syntax evaluator. Firstly, I would like to say that applying syntax evaluator does mean that we just do not compress some of the sentences. So it may seem nice, and it's usable in a real system when we do not have to compress every sentence. We want to compress only those in which we are sure, and the others can stay. But it shouldn't be seen as a panacea, because some sentences remain uncompressed. And we can see that applying syntax evaluator, and so selecting only those sentences which are considered correct by syntax evaluator, results in better performance for any model. And the same results can be seen for human evaluation and even for goal data, because if we remove those syntax evaluator, those sentences considered by syntax evaluator as wrong from goal data, we will still get a small gain in readability and informativeness. You can see that 35 sentences of 150 test data in human evaluation were removed by syntax evaluator, despite the fact that they are goal data. The difference between using syntax evaluator and not using it is high for initially bad models, and for these models the syntax evaluator does remove more of the sentences. So you can see, for example, that for multilingual BERT model, 1 of 3 sentences approximately is removed, so it's not compressed, because syntax evaluator does think that compression is wrong. And this inevitably results with increasing of compression rate, and we get a very high compression rate for any combined model with syntax evaluator, which can be bad if we want to compress compressed sentences higher. But if we really would like to remove only some of the words and have a clean and nice text with no mistakes, so remove only what is absolutely necessary and where we are sure, using syntax evaluator can be a good choice. Here are examples of how does the system works. There is a source sentence, and you can also see its compressions by different system. The most fun of this compression of multilingual BERT system, because it's a normal sentence really, but it has a completely different meaning than the source sentence, because here a robot has beaten a record and here a robot has beaten a human, which is wrong but somehow fun. And you can see star there. That means that syntax evaluator have considered these sentences as a wrong one. So it would not allow to compress it in some such way. Which user is good, because that's a wrong compression. And then to another example. К тому времени Фрида уже не могла встать с постели, and it's three compressions by different system. Фрида не могла встать, Фрида могла встать с постели, и Фрида уже не могла встать с постели. And you can see that Russian verb compression is definitely wrong, because the meaning is changed to the opposite by removing negation, but syntax evaluator doesn't see it as wrong, because in universal dependencies tree theory, negation не is dependent on its verb, so it's child of могла in the sentence, and its removing is completely grammatical. And to truth be told, we do get grammatical sentences, but this is wrong sentence, wrong compression, because the meaning is changed. So this problem probably can be solved in future by merging negations to words, but it also would require appropriate source embeddings if we used a model initialized with embeddings such as Russo-Torres models. And then to conclusion. As a result, a corpus for sentence compression in Russia was collected, prepared and evaluated. Experiments with several models conducted, namely LSTM, Russian BERT and multilingual BERT, Posthoc syntax evaluator implemented, and automatic and human evaluation provided. And in future, I would like to do several improvements on different stages of the research. Firstly, maybe I will enrich data by more compressions, possibly translating English compressing corpora to Russian using automatic translation, and work on text preprocessing and tokenization, including named entity masking. That means that for such things as names would be masked as a one token, and then a system wouldn't be allowed to remove the part of it and to leave another part. And for the models, one of the reviewers have pointed out that it's better to use different learning rates for BERT classification layer and BERT model itself, which have shown good results for other natural language processing tasks. And I would like to try out that, and it may be a good idea to include syntax structure to long short-term model as a parameter, and maybe use other promising approaches such as Roberta. And for post-hoc processing, I think that the next step is to recover correct compression when the compression is dropped out by syntax evaluator. So not only refuse to compress the source sentence, but also seek a way to compress it somehow. So that's all from me. Then references are going. Thank you very much for your attention. Please contact me if you have any questions. Goodbye.